Higgs hunting, you probably saw this plot before. It basically tells us there's a new boson was found after 1.5 years or so of data collection at the LHC. On the left, this is the invariant mass of the diphoton distribution. And you can see there's a peak at 125.6 GeV. And the right is from the CMS, from the ZZ channel, the 4-lepton final state. So in here, there's some new discovery, new boson discovery at about 125.6 GeV. This is the breakdown to the different mode, and you can see the so-called signal strength parameters mu for different mode, dB bar, tau tau, and photon. So you can just want to emphasize that the diphoton rate is still about 1.6. The mu parameters is a little bit excess compared with the standard model one here, and all the others are basically very close to the standard model value. BB bar has still, and tau tau mode has some, is not close to the standard model expectation yet, and from Atlas. And CMS is basically the same, more or less the same story, so the diphoton mode before it's bigger than 1, now it's actually less than 1, it's about 0.77. This is the after-Morion data. So, in summary, for this new boson, basically we have a new particle or swarm, and they're consistent with the standard model Higgs. WW mode and the ZZ mode are consistent. For modic mode, we need more statistic to verify. Diphoton, we see the Atlas is 1.6 compared with standard model, and CMS is about 0.8 standard model. And the other mode, the Z-GAM mode, has not been seen yet. And regarding the spin, it's consistent with 0 plus. And other situations are disfavored. That's all we know so far from the experimental side. But for the theorists, we want to ask the following question. Suppose that we only have one light particles, Higgs boson was found at 125 GeV and nothing else. Will be found at LHC. Some people refer this as a nightmare scenario. So if that is the case, that can we say we have understand the electrosynthetic breaking? Is the standard model Higgs boson or what? Or does it belong to larger Higgs sectors? So if it's a later case, assuming the heavy guys are very heavy, it cannot be detected by the LHC, how can we be sure that this is belong to the larger Higgs sectors or even the K sectors? So these are questions that we would like to address as a theorist. So the outline of the talk is the following. I will talk about all the possible, or not all the possible, but some of the things that we have been thinking that I'm more familiar is all the different Higgs makers and its relation to the diphoton rate. And then I talk about vector photon fusion, how it relates to the get a better probe for the electrosynthetic breaking. This is based on a series of work that I've been involved in the past several years. Since I only have 25 minutes, it's clear that I cannot explain all the stuff we have done. So what I'm going to do is speak to some highlights that what we have done so far. So there are many things we can do. These are just the partial lists that we have been thinking of for uniform Higgs. Trace-domain model, many variations, and SUSY model, also many variations, radion, dilaton, and so on. These are all the Higgs mimickers that I'm referring to. So first of all, let me say briefly about each of the model. So for uniform Higgs, by definition, it does not couple to the fermions. So in general, for the gluon-gluon fusion production mechanism of the Higgs, so the top part is not there. So the dominant production mechanism for the fermion Higgs is come from a WW fusion process. So if you probe the electrosynthetic breaking very cleanly, if such kind of fermion Higgs exists in nature, this is the production side. On the decay side, for example, the diphoton mode, because there's no top quark loop in this diagram, the only contribution dominant contribution is W loop. So there's no destructive interference between the two Fermi loop and the W loop. So this can get enhanced from the W boson by itself. So the branching ratio can be as large as 10 to the minus 2. So despite we have this suppression mechanism for the production, this actually, the branching ratio can be compensated back in this Fermi case. So in fact, people have looked at this model and they find that actually the signal string can be in the range of 0.8 to 1.1 at best in this model. But the CMS actually has excluded this kind of Fermi case already for the data, and it's shown here. Another model is a very popular model, the 2x coupling model. These are shown as type 2. In this model, there are 2x couplet. So that in general, there are two webs from the usual component of the 2x couplet, and there's an angle tangent beta defined to be the ratio of the two vectors expected value, and alpha angle is the mixing between the 2x couplet and the usual component of the 2x couplet. So these are the two important angles in this model, besides the four masses of Higgs. So in this model, the fermionic coupling is going to modify by this angle ratio. For example, the BB bar is modified by this sine alpha divided by cosine beta, and W boson also to be modified by sine beta minus alpha. So to enhance the production rate, people basically look at this BB bar model in the loop and give a look at the large beta region so that they can have a large equal contribution from the Gouin fusion loop. For the decay of the gamma mode, people look at in addition to the W boson and T top quad, there's a charge loop also. And in order to maximize the W boson loop, people look at the sine beta minus alpha equal 1. So in other words, this coupling is maximized just like a standard model. So in this area, alpha goes to 0, and a large tangent beta area, in general, we can have a large, we can achieve larger diphoton rate in this model. And people have the latest one that I found is just a few weeks ago maybe. They look at this parameter space in this model, and you can see that the left, for the LS data, the left one, this red line on the left is the standard model, sine beta minus alpha equal 1. And you can see that this is the parameter space that is consistent with all the constraints for the model, and there are already a lot of parameter space in the middle region. On the right, this is CMS data. You can see that because of the directional rate is 0.7, so the parameter space is actually close to the standard model area in this one. Whereas in the LF, it's actually shift to the middle area, which has an enhanced directional rate in that kind of, in order to consistent with the LS data. So another interesting model variation of that is the intercouplet model. It's basically type 1 model, except that one of the web, one of the couplet does not have a web, the H2 doesn't have a web. So in this model, the only difference is the dielectron rate. Branching ratio, there's an additional charge Higgs contribution. So this charge Higgs can be added to the existing loop, and they can either constructive or destructive interference between the existing standard model loop. It depends on the size of the lambda 3 coupling. Basically, there is a mass difference between charge Higgs and mu2 parameters in the mass in the scalar potential, the mu2. So people can also analyze this model, and the parameter space they can have large, interesting, larger dielectron rates in this range. The mu2 parameter is very small, basically 100 to 100 GeV, and the charge Higgs is less than the absolute square of the mu2. And in this range, actually, you can see that for negative lambda 3, they have corresponding larger mu, the mu signal for the dielectron rate. Our here is basically the mu signal parameters. So the blue area is basically, you can have the values correspond to the negative lambda 3, and we have a larger diphoton rate in this model. MSSM is a popular model. As you well know, that it's very challenging to have a 125 GeV Higgs in this model, and also it's very challenging to have a larger diphoton rate in this model. And in order to do that, you have large radial correction to the Higgs mass basically come from the top quarks, the stop quarks, and this is the extra contribution to the light Higgs. So people look at this parameter space, Carena and company, and choose a very large scalar quark mass, 850 GeV and other parameters, and this will enhance the Higgs mass from the Z pole, the Z value to 125 GeV, and to achieve larger lepton rate, they need a light spark in the loop. In this case, this light quark squawk, the lepton squawk had to be 200 to 40 GeVs, and the mu parameters in this superpencil is this range. In this range, people can achieve, actually scan the parameters space a little bit, and following the Carena's work, we choose these squawk parameters and scan the lepton space, and you can see that to achieve larger lepton rate, the parameter space is shrinking smaller and smaller. And for example, you want to have lepton rate between 1.3 and 1.5, but this purple area is very small. If you want to larger, it could be smaller. So this is the trouble of the MSSM. It's the well-known trouble for the MSSM. I don't have time to explain the MSSM. Basically, here I just want to mention that there are more parameters fit, so we can have easily have easier to have a larger lepton rate, and also had the Z photon and also have larger rate in this so-called MSSM. Radion is also interesting, but I don't have time to explain details. Basically, in the Randall-Sundell Type 2, they have a radion field coming from the zero mode, the modular field, and this important thing is that this field, the radion, coupled to the energy volume stress tensor, the trace of that stress tensor, and you can have and then you have an anomalous coupling, and the gluon part enhance the production rate, whereas the photon piece actually we have opposite side. The beta function of QED compared to QCD, actually the photon piece actually will give rise to a smaller spending ratio, but the enhancement from the gluon anomalous actually help for the overall mu parameter, the mu signal strength for lepton rate. In fact, we have shown that for this range of the lambda, the scale, the Randall-Sundell scale lambdas, vary from 1 to 0.8 GeV, the signal strength can be vary from 1 to 1.5. So this summarizes what we have so far based on the stereo model that we analyzed for the lepton, the inclusive lepton rate. Basically, the standard model is 1. If you normalize to the standard model value, the signal strength. Photophobia, because it's mainly come from W fusion and very small. But the radion and the inner Higgs doublet model or generic Higgs doublet model or MSSM, they have very similar, very close together. In other words, you can have enhancement, but they are basically very hard to distinguish just by using the inclusive lepton rate. In other words, using the gluon fusion, it's very hard to distinguish the different model using an inclusive lepton rate. So that naturally brings us to the next topic, the vector boson fusion. So as I mentioned, vector boson fusion is a dominant mechanism for the Higgs, and because it directly probes the electrosignature breaking. So Here's a plot. So in the main thing is that in a W-gluon fusion production of the Higgs, there's a two forward jet, very energetic forward jet, that experimentalists can be tagging on these two jets to give you more information to distinguish between this mechanism and the normal gluon fusion mechanism. Because in the gluon fusion, it's very hard to isolate the electrostatic splitting effect because kind of a loop. Any color particle can contribute that. Here is a tree process, so you can plug directly to the WW the gauge sector, the electrical gauge sector. The thing that need to place the price to pay is the gluon fusion is basically the dominant mechanism. The cross section at L6 TeV, ATeV is about 20 picobars, and the metal fusion is about 8% of that. And the Higgs is even smaller, 5%, and the TD bar top Higgs. TD bar Higgs will be 1%. So it's a very smaller cross-section to start with, but it might be important to isolate the two different processes. In the inclusive, we have studied, we see that we can not be able to tell the difference between the different Higgs mimickers, but maybe you look at jet diphoton, the exclusive event, you can be able to do something. The hope is that at least we have, maybe you can do something to distinguish the different Higgs using the jet two-photon event. So in this case, VBF, the metal-gluon fusion, and other associated production mechanism will be very important. As I mentioned, we can use the forward jet tag to suppress the associated production. So maybe we can combine these two different cuts. You can be able to tell more about the nature of the Higgs. That's the idea. So the VBF selection have been known for a long time. So we impose large energy on the jet, and the rapidity gap that we have just learned from David's lectures. The difference between the two jets is large, and the important thing is that also that the two jets have to be in opposite directions. So the eta of the two jets, the product of the two has to be negative. So this is a well-known cut that people use to separate the VBF with the gluon fusion. And also for the two jet, the large uranium mass like 500 GeV imposed can help you to distinguish or to suppress the associated production of the W with the Higgs, because in this case, the uranium jet mass of this coming from W and Z is basically picked at the MW mass or the Z mass. So we can impose a large cut on that one will suppress this associated production. So the strategy we have is that we first scan in each model that we're interested. We scan the probability state to have this the mass 125 GeV for the Higgs, and then we want to have the diphoton rate is at least as big as the standard model, bigger or larger or equal to the standard model for the dielectron rate. In that parameter space, we calculate the VBF cross-section and compare to the standard model VBF. So in addition to the jet cut, we also, of course, have to impose the cut of the diphoton, to think of this is the Higgs has to have this diphoton in the final state. So this is obvious. And then we have used this PVF to do the pattern showering and hydrogenization, and use the PVF BGS to do the detector stimulation, and so on. So this is the result that we have doing the comparing the inclusive basically coming from gluon fusion and the exclusive coming from VBF, and trying to this is the mu, the signal strength for the different model, and you can see that the difference is the most important effect is on the radion model and the Fermi-phobic model. In the Fermi-phobic, as I mentioned, its dominant production is for VBF, so it's very large. And it's basically an two-part experiment using this VBF. But unfortunately, all the other model, like the Twix-Toppan model, MSSM, basically is also clustering, is still clustering all together around the one area. So it's still very hard to use VBF to distinguish the all these Higgs in these different models. Radion is small, so it's still maybe unlikely to form if you compare with experiments. So this is basically that's what I said. So if in summary, so if similar inclusive rate for the last access in the exclusive digest and two photon, then it would be a Fermi Higgs, but have to go out experimentally. On the other hand, if a similar rate of access is seen in inclusive production, but a very small VBF production rate, this could be a radion, but it's unlikely. On all the other cases, it's very hard to distinguish between among the inertial subret or two subret model or MSSM and so on. Maybe I should mention that before the atlas is about 1.8 for the mu gamma, but then it's dropped to 1.6. This actually helped the MSSM a little bit because MSSM, as I mentioned, is very hard to get large direct photon rate in that particular model. So the last topic I want to mention is WW scattering. This is, as I mentioned, as you see that the VBF is very hard to distinguish the various Higgs mimickers in the diphoton channel. But this channel may be interesting. The WW scattering is a tunable process, and it's well known that the gauge diagram itself cancel the e to the fourth back energy behavior, and the Higgs had to be introduced in order to cancel the e squared term, the energy squared terms. So it's very sensitive to actually, I don't have time to show details. This is the gauge diagram at high energy behavior behave like e to the fourth, and they cancel by itself and add up all the diagrams. The left over the e squared term may be cancelled by the Higgs term in here, in this term. So the cancellation is dedicated. It depends on the gauge structure as equal to cos U1, and also depends on the Doppler structure of the Higgs boson. So if there's anything new beyond the standard model, this scattering amplitude may be useful to use to plot the underlying structure of the electrostatic braking, whether it's coming from a single Higgs subret or other something more. So suppose we modify the coupling to the back boson deviation from standard model by a small factor square of delta, and you can see that the e squared term will no longer cancel, and this can happen, for example, in the twist-coupled model. As I mentioned, the coupling is going to modify by sine beta minus alpha, and a goal fitting analysis by Kingman and his student, basically the existing data basically constrain this deviation about 0.96 with the last error. So it's very close to standard model already. But such high energy behavior, bad energy behavior can be explained, can be translated to a unitary violation, which can be shown clearly by looking at the partial wave amplitude. Some years ago, we looked at that in this partial wave, and you can see that the partial wave, for example, if you choose the deviation about 0.8, you can see the violation of the partial wave A00 is about more than 2.5 TeV. So this is a theoretical curve. You're not going to measure it at LC. So maybe some other thing you can do is look at the WW scattering to say at the intermediate scale, maybe you can show up some enhancement in the scattering of the WW scattering. And this is what we did recently in a generic, actually in a realistic twist-coupled model. You look at the WW scattering in these 4 different processes. For example, this one is W plus W plus minus in the final state. So we divide to L plus and L minus plus 2 neutrino. And this is the 2 lepton invariant mass distribution of this process. And you can see that the black curve is the standard model, and the red curve is this deviation of the standard model. You can see some enhancement. And similar thing you can see for the other channel. And the electronic cut, I'm just showing here. I'm trying to tell you details. So, enhancement you can see the distribution, but if you look at the number in the cross section, it's not that expensive. The more impressive one is the ZZ mode for the four lepton and final state. You can compare the standard model, it can be almost double that one, but the rate is very small in terms of P2 bar. This is the 10 to the minus 3. So even with 300 inverse Fresnel bar luminosity, this only gives you a few hundred events. So this is something that is not impressive in terms of cross section, but in the distribution, very interesting. So let me conclude. Despite a standard model like Higgs is fine, so many possibilities still possible to explain this resonance. So we need more data to distinguish. So I think BBF, the vacuum boson fusion, is the next important production mechanism for Higgs, because it can help us to distinguish different models of Higgs, and also it can be useful to probe the electroweakness splitting directly. I'll stop here. Thank you.
Questions?
Yes. So you have considered radium as the Higgs mimicker, but in the original setup, the radium is in addition to the Higgs boson, right?
Right.
So if you consider both of them and consider the mixing,
between the Higgs boson, electron, and also the radium, the people have considered general mixing between the three. Then you'll be have better shape, you'll be more parameter too. So you're right. I don't have the time to go into other version. Yeah, you're right. People talk about this mixing between these three different things, but the mixing is come out of is arbitrary. Anyway, yeah, that's a good point.
So the data is coming back more and more like a standard model.
Yeah.
So you have a better, mini curves.
Yeah, I think it's getting close to the standard model. So it's very. So you can see that the enhancement is it's not very impressive. Like this relay is not it's small. So I think you need a lot of luminosity or data. So I guess you're right. I mean, it's very depressing for theorists.
Okay. Can I have a last question?
Okay. If you say you want to measure the vector boson fusion with two forward jets, but in fact, this Coulomb fusion can also contribute to the same process, right?
But they don't impose any particular. That's inclusive. The inclusive will in principle will include all the things that you mentioned. But if explicitly put a cut on it, then will basically suppress the part coming from the muon fusion. The cut that people devise is basically isolate the BDF from the others. You're right. In the muon fusion, there's also two jets, but they're not. It's not to be more energetic than the one. They are really more energetic, still energetic, but the cut that we impose on the eta is single out the BDF.
All right. Next speaker.